Wonderful. Thank you, everybody, for joining us today for our February public event. It feels like it's already March for some of us because it's been a long month so far with all the cold more than anything else. We are proud to have with us today one of our friends at the center, Tony Moffat. He's going to be giving us a talk on his career achievements in astrophysics. But before he does, I'm going to ask David Levy to start us off with a welcome reading. David?
Well, thank you very much, Kareem. It's really good to be here again. And I'm very excited, as I'm sure we all are, to hear Dr. Moffat's lecture. I've known Dr. Moffat for many, many years, and I'm really excited about hearing it. We're really all excited. Also like to welcome Peter Jedicke, former National President of the Royal Astronomical Society of Canada, and visiting now in Arizona, which has become unofficially a Canadian province, part of Montreal. Excuse me. I'd also like to introduce you to my telescope, newly renamed telescope, Vega, which is right here. And with Vega, I can actually look outside through the open window, as I've been doing. And anyway, my theme tonight is going to be about darkness. Not the darkness that we all think about when we think of darkness, like the sounds of silence, hello darkness, my old friend, but the darkness one thinks about when the sun goes down and the night sky begins its nightly friendship visit. And in order to celebrate that, I'm going to quote tonight from Thomas Gray's Elegy, written around 1751. The curfew tolls the knell of parting day. The lowing herd winds slowly o'er the lea. The plowman homeward plods his weary way and leaves the world to darkness and to me. And now, Kareem, back to you. Thank you.
Thank you so much, David, and it's good to see you again. It's been a little while. I think Frank was mentioning just as we started that we haven't seen you in a bit. For those that aren't aware, David Levy, the famous comet hunter, is our honorary president of our society. He's currently living in Arizona, but he joins us for a lot of our online events, which has been one of the nice, pleasant parts of COVID, is getting to see David and others a little bit more often. I'm going to, before I turn it over to Tony, I just want to make a couple of comments. The first thing that we want to do is we want to make a land and sky acknowledgement. In the land and sky acknowledgement, we very much want to recognize that we are on unceded territories here in Montreal and here at John Abbott College, where we are hosted for our library, the I.K. Williamson Library. We tend to recognize a lot of the First Nation stories and traditions, and one of those is recognizing that the moon of the specific time of the lunar month is recognized by what's happening in nature. So the Mi'kmaq moons would call this, or the Mi'kmaq tribe would call this current moon that's just started waxing the maple sugar moon. The Cree and others would call it the eagle moon or the crow moon, recognizing that the birds are going to start making noises as the spring starts to come around. The Sioux actually call it the crust on the snow moon because you start to get to these melts that followed by the sudden freezes, which of course make driving treacherous for the rest of us settlers here now. The RASC, we're proud to be a part of the Royal Astronomical Society of Canada. It's over 150 years old and our center is over 100 years old. We are a large center relative to some of the other population centers around the country. Not as large as somewhere like Toronto, but we're boasting 170 plus members and a lot of them are very active in our events. With the RASC, you not only get to do outreach and events like this, you get to have astronomical evenings under the stars with others that enjoy the hobby with us, and you can pursue certificates such as the Explore the Universe or the I.K. Williamson Lunar Certificate. Our Montreal Center has this wonderful library that we have here at John Abbott, as well as an observatory at Morgan Arboretum with a 14-inch telescope. We have another observing site down near the southern side, close to the US, called Woolly Woods with a 16-inch light bucket that we cannot wait to get back out there once the weather turns. And we have monthly events for the public as well as bi-weekly events for members. In fact, our members events, a lot of them are still online, but we do have some observing happening at Morgan Arboretum when Wednesdays and Saturdays are clear. And we have our library nights at least once a month. And our next one is going to be 1 month from today, Thursday, March 23rd, here at the library. And Nicole, our member liaison, is going to lead us in some constellation sketching. So we're going to get to actually, hopefully, if the weather's good, go outside and do some live constellation sketching, which will be fun. Our next in-person event is going to be led by our outreach coordinator, Russell, and it's going to be a full moon astronomy evening next Saturday at Verger-la-Bonté in Il Perrot. If weather's not good, we're still going to be there with our outreach materials and with some astrophotography to put on display for the people who get to join us and enjoy a night under the stars. Our next talk will hopefully be later on in March, and it'll be a postponed talk from March 13th, 2020, the day everything shut down. One of our directors, David Schumann, had prepared a talk on space places to go and visit during the summertime. So we're hoping to bring that back in now that we can actually plan ahead to go and visit in the summer. And then in April, we have a public event on April 5th, which is a Wednesday at 7 p.m. here at John Abbott. And it's going to be a call-in live from Hawaii, from the Canada-France-Hawaii telescope operator, Dr. Laurie Rousseau-Neptune. And she is the first Haudenosaunee Inuit astrophysicist graduated from Quebec. And she's going to be joining us to tell us a little bit about her research and her story. Now for tonight, we have another incredible astrophysicist, one who just won the Beals Award last year from the Professional Association of Astronomers. And he won the award for his lifetime achievement in astrophysics. Now we've been lucky enough a few times at the RASC to get glimpses of some of Tony's research into massive stars. So tonight, Tony's going to join us and tell us a little bit about his journey through astrophysics and his love of massive stars. Tony, I'll turn it over to you.
Okay, I'll start sharing my screen now. 2 clicks and we're there, I hope. Is that okay now?
It's perfect.
And can you hear me okay?
Loud and clear.
Good, excellent. Well, it's a delight for me to do this evening, especially after having just celebrated my 80th birthday. And I'm 15 years into retirement, but I can't stop doing astronomy. It's just impossible. The passion that I've acquired over the years just continues on. I just wanted to show this picture of a beautiful star cluster that was observed by the Hubble Space Telescope. It's in our own galaxy. It's not so well known by most people, it's perhaps especially amateurs, unless you're in the Southern Hemisphere. It's not too far from the Carina Nebula, NGC 3603. And in the central blob here, there are at least 50 O stars and a couple of Wolf-Rayet stars in one parsec, which is about 3 light years across. So that gives you an idea of sometimes the extreme nature of these objects that like to form together, especially massive stars. And of course, there's a whole flock of low mass stars along with it, following the initial mass function, the IMF as it's called. So let me start. Let's see, I have to press the arrows. Oops. Oh, it's not working. Okay, just a sec. Oh yeah, there we go. I put the emphasis on intuition, using one's own intuition, because that's how I function. That's how we come up with ideas, and you look at something and you say, it has to be like that. And it's related to having a hunch or insight. And this has worked for me anyway, very well over time. And what led me to astronomy are 2 things. First of all, events that happened. I'd quote just 3 here. Even at age 5, I can remember looking out the curtain from my bedroom and seeing the moon, and then later looking out and seeing it had changed position. This was a revelation to me at the time, at age 5. Of course, nowadays, it doesn't really mean so much. And then when I was 10, I had my first look through a small telescope of a neighbor, and I saw these craters, and I thought, my God, yeah, it's obvious what that is, And then when I was 15, I was lucky my father took me to the David Dunlap Observatory for a visit. And of course, along the way, both in high school and university, I've had excellent teachers, and elementary school as well. which certainly helps. Anyway, I just wanted to contrast myself with the normal way things go. Other people, other astronomers, professional mostly, start from small and go to large stars, to globular star clusters, to galaxies, and even cosmology often, not always, but often. In my case, it was the opposite. I started a master's thesis at U of T, University of Toronto, on the Andromeda Nebula, looking for Cepheids, and then I went back to open clusters and galactic structure, and then finally to massive stars. So from big to small. But with respect to massive stars, which were not too popular in those days when I started in the 60s and 70s, that they have become, in their own right, a very important element of the universe. And they're being probed by the Webb telescope now as we speak, essentially. And in addition to that, of course, massive stars, because they're so bright, they dominate the light from star formation galaxies. But of course, they're also important for producing huge winds of material ejected. They're important in stellar evolution, pre-supernova, gamma ray bursts, black holes, formation of black holes mostly, even the lower mass ones, neutron stars, and gravitational wave sources. And the list goes on. So let me say a couple of words about Beals, Carlisle S. Beals. He lived, for 80 years. Whoa, I'm 80. I just turned 80. Oh. Anyway, his early years were at the Dominion Astrophysical Observatory in Victoria, where I worked for a summer in 1964. His expertise was in the interstellar medium, and he worked on hot luminous stars, including Wolf-Rayet stars, which are of great interest to me. Later, he moved to Ottawa at the Dominion Observatory. He became the director, and he's most known for his work on meteor craters. And some of his awards are listed here: Fellow of the Royal Society of Canada, Fellow of the Royal Society proper in the UK, 4 honorary doctorates, and he's an officer of the Order of Canada. And even an asteroid was named after him. So this is a huge achievement. So let me just outline what I consider my highlights. My wife warned me not to toot your horn too much, so I'll toot my piccolo instead, if I may. Anyway, in all of these, I would claim that insight started me off in virtually all of them. And it started off after my master's thesis. I went to Germany to study. I lived there for 10 years, and I did both doctorates that you can get there. And my doctorate work, first part, was on star clusters, open star clusters. And then I evolved a bit to slightly larger scale galactic structure and dynamics, for which open clusters are good tracers. And then I switched to massive stars because I wanted to know more about the physics of what makes these stars work. That was the fascination I had. And here a list of some of the things I've worked on, which I will enter into more detail as I go along. And then I've dabbled in intermediate mass stars, which is more or less a sideline, and in particular novae and related dwarf novae, central stars of planetary nebulae, and young stars. So let me get started. This is what I did for my thesis. On the left, you see an old photograph of M31, the Andromeda Galaxy, taken probably at Mount Palomar in the 20s. And on the right, you see a picture taken with the world's largest Schmidt telescope that Sidney Vandenberg obtained when he went to East Germany, Tautenberg, where it's located, and obtained a huge number of plates of M33, M31, and other things. And when I asked him if I could do my master's with him, he said, yeah, I've got a whole bunch of plates of M31. Go and look for the Cepheids. See if you find more than Sandage and others have found before. So that was my project, blinking plates. But I found it kind of boring, and I didn't stick with that work. I evolved, as I said before, to smaller objects. And the first thing I did was, for my doctoral thesis in Germany, was to look at a number of young open clusters on these on Hamburg-Schmidt plates. The Hamburger-Schmidt is a smaller Schmidt telescope, but it's where Bernard Schmidt used to work, and he invented the Schmidt telescope. And there's a model of a telescope that he made. The first one he made as a model, it's on display there. It's about, I don't know, maybe 30 centimeters across. It's just a small scope, and it actually worked. And the idea took off. And we don't hear much about Schmidt telescopes nowadays because there are huge detectors which can capture the whole field without the Schmidt principle. Anyway, I had photographic plates to work with, and to measure the brightnesses of stars was a tricky thing in those days on photographic plates because the photographic emulsion is nonlinear. That is to say, when you measure the size of the star, the blackness of a star, it's not directly proportional to the intensity. You have to work with that. And I had to work out a way to get around that so I could extrapolate the calibration based on photoelectric standards that were observed in each of the clusters. And I show here an example of a black star. This is what a star would look like, although a fuzzy edge is not so perfect as the one I show here. And the variable iris photometer is a way of measuring the size of, essentially the size of this black dot on the plate. And with the radius d, the integral of the transmission, the degree of blackness across, which would be very low in the center, almost zero, to the edges where it would pick up, would give you, out to radius b, would give you, and assuming this was constant, that's the principle of the variable iris photometer, it gives you a measure then of the size of the black dot on the plate for each star. And the trick was, of course, to convert to intensity and work from there. And I invented a function based on the stars with known magnitudes on the plates. And I came up with this function, which is very similar, and it's called the characteristic curve. And you can see down here an example that it fits almost perfectly, the data. And that this is just an example of all the other data. It fit very well with these parameters that I mentioned here. And it was very important to note that all stars have the same point spread function, PSF, I've written down here. Those of you who have worked in bad seeing know what a point spread function is. It's normally the stars are point sources when they arrive in the upper atmosphere, but the light degrades very quickly, and it be due to turbulence in the Earth's atmosphere, and they become a finite point spread function. You can't know where the star really is other than the center of the image that you have. So the next step was to find an expression that relates the transmission, the degree of blackness, with the intensity that caused it in the first place. Sorry, I missed that. Is there a question? No? Okay. Anyway, this is the function I came up with. It's sort of like a Gaussian, yet it's a little different. And the relationship between the magnitude of the star and the intensity is given by this, and it's a function of the radius. And this is now known as the Moffat function from my publication, one of my first in 1969. And it's the one I've had the most quotes for. It can be applied universally. Almost all images that are obtained with telescopes, be it on the ground or in space, like the Hubble Space Telescope, have used this. And I claimed a bit of fame overnight, but much later than the project. This happened, I think it was recognized first in the 80s, even though it was done in the 60s. And just as a note, for this parameter beta up here, when it gets very large, the function degrades into a Gaussian profile, which was what people had always used up until then. They're Gaussian images. No way, it's not at all possible. And for beta equals 1, you got what's called a Lorentzian function. And over here on the right, you see the actual function with actual data that I obtained using photographic plates. many young people find this unbelievable. How could you ever do that? How did you have the patience to do that? Well, I did. I had to do it. I had to succeed, and it was the only way to do it. I had to calibrate the plates. And the proof is in the pudding, as they say. And these are the results. These are the calibration curves with my extrapolation of the model compared to the data. And this allowed me to extrapolate down to fainter magnitudes, which would not have been possible with the photoelectric standards that were measured, of which you see a few here. Here's an example played in the U band, ultraviolet, ground-based band, and visual up here. And the shapes are quite different, but significantly fitted with this function I invented. Okay, so, but as I said, the proof is in the pudding, and you want to look to see what kind of work this gave. And these are color magnitude diagrams of two clusters, one very young on the left and one much older, about 100 megayears, 100 million years on the right. The one on the left would be only barely a handful of megayears old. And you can see that in the young cluster, on the left here, even the pre-main sequence models fitted very well the data that were obtained. There's a lot of scatter here. With CCDs nowadays, you would have much more precise magnitudes without so much scatter. Anyway, and then this older cluster, the same thing. It's too old to show pre-main sequence stars down to the magnitude I observed. And indeed, the 0H main sequence that was fitted looks pretty good here. The circles are are mean values instead of individual stars, as they are in the upper part. So that's just an example. And here are real photographs of the two clusters. The young one on the left, which is typical, there's gas still lingering around. And on the right is the older 100 megayear cluster, I guess like the Pleiades, although without the gas that you see in the beautiful Pleiades. Anyway, let's move on. After this, I went to observe with our 60 centimeter telescope in Chile, 2 months each time, solid every night for 2 months. I did this 3 times in these 3 years in the 70s. And my task was to obtain photoelectric photometry, precision photometry of young open clusters. And this was done 1 star at a time, which people laugh at this because now with CCDs, you can obtain linear data for many stars at once, although the detectors are much smaller. And anyway, this project led to a new spiral map of our own galaxy, which I won't even show because it's not so great, really. And the photoelectric sequences I obtained in these clusters were allowed us to calibrate the open cluster photometry that can be used on CCDs nowadays. Today, you need standards. You can do it without standards, but it's a tricky business. You have to observe standards sometime in the night from the ground because you have the Earth's atmosphere to cope with, and that makes things much weaker as you go lower in the sky. So you have to allow for all this, and it's color dependent, so on and so forth. It's a complicated procedure, but if you have standards in the cluster itself, as I obtained, you can do it much more quickly. Anyway, with radio velocities obtained from stellar spectra of some of these clusters, we obtained the first rotation curve of our own galaxy, this paper here, and it showed it was a flat rotation curve, even though the curves here give omega, which is V over R, which is omega is the angular velocity. And for the rotation velocity of, I've shown here for 300 and 250, that's about the best you can do with these data. This is the first proof that our own galaxy shows a flat rotation curve, which is quite relevant for dark matter, as we now know. But this work was more or less eclipsed by that of Vera Rubin, who obtained with just a 1 exposure with a spectrograph with a slit along the length of the galaxy, rotation curves of many spiral galaxies, and reached the same conclusion. But Nevertheless, it's useful to know that our own galaxy behaves the same way. Anyway, when I started to do massive stars, it struck me that maybe they vary more than we think. And the first direct discovery of the fact that hot star winds were clumped, they weren't homogeneous and smooth, came from our work from the Université de Montréal. And with this work that required a revision of the mass loss rates, M dots, we call them, by a factor of 3, which was changed our interpretation of the evolution of these stars enormously. And the first hints actually that there was clumping came from polarimetry, which I did, or which students of mine did in Chile. And here you see 3 examples: a Wolf-Rayet star, which has a very strong wind and lots of free electrons, which scatter the light and polarize it coming from the star. But if the star were perfectly spherical, everything would cancel out. And like this star, you wouldn't see anything. These are the Stokes parameters, Q and U, which are the components of the linear polarization, essentially. But another star showed wild variations, completely stochastic, random. What's going on there? And then another star, which was a known binary, showed a beautiful double wave, which is understandable if you treat the Wolf-Rayet as a source of free electrons, which scatter the light from the O star as it moves around. It goes through a double wave because you can't distinguish polarization on one side from the other. That's why it repeats in a double wave like this. But the star in the middle was the first real indication to me that something was going on in the winds that we didn't know about before, clumping. So the next step would be to look with the spectrograph, in this case with the Canada, France, Hawaii telescope on Mauna Kea, Hawaii. And we obtained the first, this is data from one night, and you can see the bumps which change with time on this particular star. This is WR134 in the Cygnus, one of the 6 known Cygnus bright Wolf-Rayet stars. Wolf-Rayet stars have the advantage that they have, whereas O stars have, like this O9 star, Ken Lacerte, has an absorption line. This is helium-2 at 5411 angstroms. And at the same place, this Wolf-Rayet star this is the same transition, but it's a huge emission line coming from the whole wind. And it's because of the expansion of the wind that the line is broadened, Doppler broadened. On the left, it's the stuff coming towards us, blue shifted, and on the right, it's stuff going away from us in the wind behind the star at quite a distance from the star, actually. And here you can see the tracing of features as they vary with time, going from time increasing downwards. And those features that started on the blue side became bluer, so they were accelerated with the wind itself, and those on the red side became redder. So this interpretation is quite simple, and they change in intensity too. The clumps grow and then they die away, or perhaps we catch one that's just dying away and another one comes up. So this was a very important discovery, as it turns out. And my colleagues around the world are now talking about clumping. It's a nuisance, of course, in many ways, but it's also has its benefits. They act as tracers of the wind. And if this wasn't enough on Wolf-Rayet stars, which have the strongest winds, we looked at, finally, with one of my students, Thomas Eversberg from Germany, we went and used the Canada, France, and Hawaii telescope to look at an O star in the southern hemisphere, no less, at declination of minus 40 degrees. And from an observatory of plus 20, this means it was never higher than 60 degrees from the zenith, which is a bit of a challenge, but it's a very bright, it's a second magnitude star. So you can observe it almost with your eyes closed, although it was tricky. And here are the data displayed in a slightly different way. And you can see the emission line only goes up to about 20% above the continuum in this emission line in the star. This is the optical part of the optical spectrum. And these are the deviations from the smoothness, from the mean profile that was shown below here. And you can see there are things going out in the wind, and those are clumps. So this is the first time that an O star was revealed to show clumping. And now we believe that all hot stars with strong winds show clumping. It's just that it took a lot of effort. We had to have a signal to noise of about 1,000 per pixel to reveal this, which is a tall order. It was possible because of the big CCD detector that was available at the time at the CFH telescope, at the Coude focus. And then, of course, that wasn't enough. And so we went back and we applied wavelet analysis. And what you do is you take a wavelet like this is called a Mexican hat function, and you vary the width of this, and you multiply this function through your spectrum and obtain, as a function of the size, the width here, which is expressed up here in log units. You can see that as you zero in on small scale stuff, you see nothing. And it's only when you go to larger, medium, and larger scales, you start to see these waves. And that's a way of characterizing in a quantitative way the nature of these variations across the spectral line. So this was very useful. And using this information, we were able to determine that there were scaling laws. And these are very important. It means that we're seeing actually compressible turbulence. And I won't go into details here, but we found a power law with the number of clumps in the wind as a function of their flux F goes as F flux to the power alpha, with alpha about -2, which means that there are many, many more clumps when F is small. F raised to the -2 power becomes a very small number when you take F small. And so for F larger, oh, I'm sorry, that's the other way around, excuse me. I guess I'm putting you to sleep here perhaps, but when F is small, this function is large. There are many, many more features, clumps at small flux than there are at large flux. And you can convert this to mass using what we know about turbulence. And you find that the mass goes as the square of the flux of the clump that you see on the spectrum. And with the conservation of numbers, NMDM is equal to NFDF, we find a power law in the number as a function of mass. And this power law index is -1.5, which is almost identical to what we find for turbulence, known turbulence in giant molecular clouds and Lyman alpha clouds seen in quasar spectra, and so on and so forth. And even the initial mass function of stars has a similar value to this. So we're really onto something that has great implications, I think. And another power law that was found from the same data from the Canada, France, Hawaii telescope is shown here for the Wolf-Rayet star with the largest clumps and the best data. It was an 8th magnitude star. So with a 3.6 meter telescope, it was fairly easy to observe. And the big dots here are features that were seen more than once in a chain of spectra, a time sequence. Whereas the small dots are things that were only seen once and presumably random, and that's noise. And when we look in the continuum off the line, we see only noise. So this proves that these features are real. They're clumps and they're of different size, and they obey the power law, which goes, the flux goes as the velocity dispersion, the width to the second power. And this is exactly as expect for turbulence. So this was nice to find two laws that obeyed the turbulence laws and prove that what we're seeing is something much more substantial than originally found. Now I'd like to pass to another subject, perhaps a little more spectacular. Maybe you'd like to wake up a bit more for this one. I don't have any equations here. I'm sorry about the equations I use, but sometimes you can't talk sensibly without them. Anyway, colliding winds occur in massive binaries in which you have one star, for example, a Wolf-Rayet star with a very strong wind with a companion O star, and the winds collide somewhere between. You can see the shock front that forms here, and the Wolf-Rayet star blows back because it's stronger, the wind, and due to the orbital motion, you get a spiral that forms like this. And if the Wolf-Rayet star has a lot of carbon in it, it's a WC star, then you'll find dust grains going out like this in a spiral. And we see systems like this, as I'll show in a minute. And another thing we found, this is the work I did with Sergei Marchenko, who was a Ukrainian astronomer who worked on exactly the same things as I did. We discovered this through email, and I even visited him in Kiev in 1989 and 1990. We observed together in Uzbekistan, one of the former Soviet republics. And just recently, 6 years ago now, we've made a discovery based on spectra from the Gemini telescope, the south, of what are called polycyclic aromatic hydrocarbons in the spectrum of some Wolf-Rayet stars that form dust. And this is what you need to form carbon dust, which is in the spirals that we see. I won't go into details because it's a bit complicated to explain. But anyway, we compared our spectra. We see the absorptions where there are paths that were seen exactly the same way in the Orion Nebula and other areas in the sky, which are well recognized to show these polycyclic aromatic hydrocarbons, which are it's actually found in perfumes. Anyway, this is what we discovered among some of the images, and believe me, the surface observers on the Gemini telescope, they knocked their socks off to see this image. What is that? They said. They couldn't believe it. You see 5 repeats spiral. This is as part of a spiral. And the arms of the spiral are not equal because it's seen in projection. And the shock cone between the two winds is rotating around. And the observer is sort of in the plane of this. So it makes it complicated. You don't see a simple spiral like the picture I just showed you earlier. It's a bit more complicated to interpret. And it was only recently that my colleague Lau et al. Have solved this problem in detail for this particular star. And the observations, the model and the observations here are now concord exactly with the model. It's just a shock cone going around in a certain inclination, and it's just stunning for me. But even more important was a paper that we published last November. You can see that here, Nature Astronomy. We made the cover of this famous journal. It's the #1 journal. All astronomers want to publish there. And we had our JWST data, which were obtained last July at the beginning of the mission, early release data. And you can see that we have about 20, down to about here, 20 repeats of this. And every orbit that it goes around, it produces a spiral which propagates outwards. And so this beautiful image was the living proof then that this does happen. And this is very important because we'll be able to trace the dust out to large distance and see if its constitution changes in any way. The overall goal is to see how much of it actually survives and feeds the interstellar medium, which is just full of dust. And this is one of the main sources we think now of interstellar dust. Wolf-Rayet stars with carbon. The late stage in evolution of massive stars includes a WC stage where helium burning produces lots of carbon. By the time later burning occurs, it's too late. It's too short-lived to reveal itself at the surface of the star. So we just see helium burning, carbon atoms coming out, dust emitting from the carbon produced in the form of dust grains. And another project I'd like to highlight is this O star. Again, it's an O supergiant known as Zeta Puppis. It's in the southern hemisphere. Most things are in the southern hemisphere as far as massive stars are concerned, because it's very much busier, because it includes the galactic center, the inner part of the galaxy, which is very rich in stars anyway. And one of the recent projects I've been a team member of is the BRIGHT mission, which is originally six actually, nano satellites about the size of a car battery and the weight of a car battery, 7 kilograms, in space. And each one of these satellites cost about $2.5 million, which is cheap by astronomical standards for space. And it's produced wonderful results, as I'll show you in a minute. The first thing that we discovered was that the bright data for this star shows a modulation with a period of about 1.8 days and 2 bumps occurring. And Chandra X-ray data show the same period. Here you see them plotted together for the same star. So there is a link between this feature that goes around with the star. We think it's some kind of co-rotating interaction region, as we see in the sun. But in this case, it's in a massive star. And when we look at spectra, we see that there's a delay in time as you go out in the wind from the continuum, which is closest to the star, which forms at the base of the wind, out to emission lines in the spectrum further out. And to illustrate this better, I show this plot at the left here. The continuum from the bright satellite comes from the surface of the star. And as you go out in the wind, these co-rotating interaction regions, which this is a model of them, which was made in 1996 by colleagues from the US. We think that we can match it up with emission lines which come from a cooler region, and the X-rays, soft X-rays, not so energetic X-rays, come from somewhere out here probably. This is just schematic. This is more or less speculation where this occurs. And here you see a sort of an image of what a massive star might look like. It's rather motley surface, completely unknown before. And these co-rotating interactive regions, there are 2 of them, come out like this, and it's turning around. It's this model, this artist's concept is not flattened as it would be. It would be very flat because it's rotating quite quickly around its axis. So that was an interesting discovery that I did with Tahina, who's now in Phoenix as a postdoc. David, take note. He works at the university, the Arizona State University. He's working on another satellite project with another Canadian who studied with Gordon Walker at UBC. And unfortunately, he can't come back to Canada. Visa problems won't allow him. So he's gone, unfortunately, but I'm still in contact with him. He's originally from Madagascar, a long way from home, but a brilliant fellow. I really enjoyed working with him. So another project I've been working on over the years was looking for the most massive stars in the local universe. In the beginning of time, right after the Big Bang, or a few hundreds of millions of years when star formation started, very important results coming from the JWST, all stars were very massive. This is because the metallicity, heavy elements, were not very common there, and they're needed for cooling processes. And when a star can't cool, it gets much hotter and more compact. And most of the stars at that time had masses reaching up to 1,000 solar masses, not the 100 or 200 that we find in our solar neighborhood. And the most likely place to look are in these clusters like this NGC 3603, but also in the LMC, the Large Magellanic Cloud, in an object called 30 Doradus. And right at the center of this is another cluster, but it's 7 times further away than this one. But it's very similar in look on the sky. And if you go down to the southern hemisphere, please point your small telescope, have a look. I spent hours staring at both of these objects when I should have been measuring the star. It was just mind-boggling to just see it visually. So, and this object though is surrounded by hundreds, literally hundreds of O stars, Wolf-Rayet stars. All these are very massive stars. They're being probed as we speak, essentially, by various telescopes, both ground-based and in space. But I'd like to zero in on this one because it's closer and in a sense easier, although you still need a Hubble Space Telescope to separate the stars in the center. You can't separate them otherwise. From the ground, it's impossible because you need a PSF of point spread function no worse than 1/10 of an arc second to do it properly, especially in the heart of the cluster center. So this is a color magnitude diagram showing the intensity I and the I band in this case versus the color index. And these are the main sequence stars reaching up to 3 Wolf-Rayet stars at the top and even the earliest O stars below. So these are the most luminous stars. And then at some point, the main sequence cuts off and you see pre-main sequence. These are all pre-main sequence stars going down to a little less than a solar mass. And from this, we deduced an age of about 1 million years. This cluster is very young. It's very young. And the spectra of these objects is also revealing. In the O stars, you see lines of helium-2, doubly ionized helium. This requires temperatures of above 30,000 Kelvin at the surface. And in the Wolf-Rayet stars, some of the lines change from absorption to emission because the winds are so strong. And these stars make themselves known by their strong emission lines. And this is due to their high luminosity, which drives stellar winds. It's mostly the ultraviolet light in those winds, in these very hot stars, that drives the winds. And the process of wind driving is something that's a bit complicated. It wouldn't be easy to talk about. I'm not going to talk about it here. Just to mention, empirically, this is what we see. So the most massive stars in the local universe are of type WNH, which means nitrogen-rich Wolf-Rayet stars with hydrogen. The spectra show Wolf-Rayet-like emission lines due to their high luminosity. And they're actually main sequence stars with hydrogen abundance, which is essentially solar, perhaps a little less in some cases. And these non-classical hydrogen-burning Wolf-Rayet stars, the classical Wolf-Rayet stars are helium-burning, and they produce carbon and nitrogen that we see in the winds. But these non-classical are really very young and luminous stars. This is a new discovery. And later, of course, we wanted to measure their masses because there were a couple, there was one binary right at the center of this cluster, NGC 3603. And we got time to do it with the Hubble Space Telescope. But 1 week before we went to the observations were supposed to start with the Space Telescope Imaging Spectrograph, STIS, this instrument died. Its death lasted for several weeks, if not a month, something like that, back in 2004. And so we're left without data. And we scrambled around and used the ESO, European Southern Observatory, instrument from infrared spectroscopy to obtain several visits over several months to nail down the orbit. And just take a look at this. The central brightest stars, they're all these 3 Wolf-Rayet stars. This is all in 1 second of arc. So you just can't do this from the ground. You need Hubble or some telescope like it. And the spectra of some of these stars are shown here in the infrared, near infrared, at 22,000 angstroms. It means 2.2 microns approximately. And you see similar lines as you see in the optical, which we showed a minute ago. Anyway, this is the orbits of the 2 stars that revolve around each other in a period of just under 4 days. And from the light curve, which was obtained with Hubble data, NICMOS to be more exact, in the near infrared showed a double eclipse. And this was useful because it gave us access to the inclination of the orbit, 71 degrees. So with the observed radial velocity variations of each star, one denoted in red, the other in blue here. We deduced the amplitude of variability in kilometers per second for both stars, star 1 and star 2. They're very similar. And we obtained masses of a little over 100 solar masses and a little less than 100 solar masses, but with huge errors because the data are not precise enough. If we'd had Hubble data, we could have done it much more precisely, but we didn't. And we didn't try again because the student left for a postdoc in England, and he was doing other things at that time. So this project remains in limbo, unfortunately. You can't finish everything you want to, always. And the question begs, what is the upper mass limit in the local universe of stars? And Don Feiger, in a paper in 2005, published this work based on the Arches cluster, which is one of the 3 bright clusters near the galactic center, only visible in the infrared. In the optical, you see nothing here. And he was able to determine statistically the number of stars per luminosity interval down to this limit here. And below that, he saw no stars. Whereas if you take the initial mass function that's normally adopted, you would expect either this relationship or this one here you expect stars to be found here. None were found. This implies that the upper mass limit of star formation in the local galaxy, here in the center of our galaxy, is around 150 solar masses. But this is not the end of the story, because a little later, a theoretical paper came out with some of my colleagues. This is the guy that I had as a doctor student, a German. He went to work with Paul Crowther in the UK, and they came up with a theoretical limit, which was about 300 solar masses. But it's theoretical. And my view is that theories come and go, whereas observations are forever. So it remains to be seen. You need a binary to prove masses anyway. I wouldn't trust these masses, and the jury is still out on this. By the way, this is the 30 Doradus. This is part of the LMC, Large Magellanic Cloud, is as you would see it in the sky, is here. And 30 Doradus is the brightest object and the most massive of its kind in the whole local group galaxies, which includes our own galaxy, M33, M31, and a bunch of other smaller galaxies. It's just huge. And here's a blow up of the same region. And in the very heart of it is this object Radcliffe 136, which is a very dense conglomeration of massive stars. Anyway, let me pass on to another famous object, Eta Carinae, which is a very beautiful object. At first, it was the Hubble images were spoiled by the bad optics you heard about in 1990. They were corrected, and this is after the correction. So it became sort of immediately obvious what's happening here. The central star, actually what turned out to be a binary, produced an eruption back in the mid-1800s, and it produced a bisymmetry, the ejection of material along the polar axis, and even a skirt around the equator. And this object is located here in the heart of the Carina Nebula, which you don't see from the north. You have to go the south hemisphere to see it. But it's interesting that before Hubble was repaired from the ground, you would see it like this, and it was described as the homunculus image, the little man. And I've shown down here from after my visit to the Museum of Natural History in London, they showed what parts of the body would look like if they were the size illustrates the sensitivity. Our hands are huge, for example, and the lips and so on, which I found, they call this a homunculus. Anyway, you see that at the same scale with Hubble, this object has now been resolved. We know much more about it. And I'm on a team with Ted Gull. There are about 25 of us from all different phases of astronomy, theory, observation, X-rays, optical, infrared, and so on. And we have meetings every 2 weeks by Zoom and discuss the latest findings, and it's just wonderful. This keeps me alive in astronomy. Now, this is the light curve of Eta Carinae back in the 1800s on the left here. And you can see here that at this date here, 1850, just before 1851, actually 1840s, the Eta Carinae became the second brightest star in the sky after Sirius, only visible in the southern hemisphere. John Herschel went down there at this time and made the first report of it. And it was believed to be a prototype non-terminal eruptive transient, that's what it's called, with a luminosity somewhere between that of a nova and a supernova. Or it could be a giant LBV, luminous blue variable eruption of a very massive star, or a supernova imposter, which we see in other galaxies, or a merger event. And as it turns out, the most plausible is the merger event, a triple system in which one star was swallowed up by one of the other stars, and what we see is a binary today. And studies are going on of this system with great intensity. There's a great competition for reaching a conclusion. And here's the light curve after. There was another mini hiccup in 1890, something like that. And then up to today, it's getting brighter and brighter. And by the 2030s, it should have reached the same magnitude as it was before the eruption. So this is a very exciting object. And today we're discussing various sources of information, from X-rays through infrared imaging and photometry with the BRIGHT satellite, X-ray, high energy X-rays, even ALMA in Chile to look on the radio has been detected, and there's other projects with ALMA coming up, and even SOAR, the Brazilian telescope at Cerro Tololo in Chile. I won't go into details here, just to mention that the VLT has seen evidence, you can see in the images here, the interpretation of the shock cone, which is formed when the wind with the star with the stronger wind pushes back the other star, it forms a shock cone. And this is what it probably looks like. It's seen by the observer. So this is very important. As we apply higher and higher spatial resolution, we can see more and more details in objects. And even from the ground, it's possible to do quite well. So the prediction is that by about 2035, because there's an object in front of it which absorbs a lot of the light from the stars, it will be so bright, third magnitude, that it will have trouble actually working on the stuff around it. So the time to do that is now, before that happens. Anyway, this is the question begs, will this be the galaxy's next supernova? It may not be Betelgeuse, it might be this one, who knows? We can't predict that, unfortunately. All we can say is that within the next 10,000 years, it will definitely go off. And finally, I'd like to discuss a little bit about my work on a nova. As a team member of the BRIGHT mission, nanosatellites, this is the Carina Nebula. Near it, as it turns out, it was announced in 2018, or just before actually, 17, a nova had erupted near this bright star. And it so happens that the BRIGHT telescopes were pointing towards this, and one of my colleagues who looks at a lot of the images as they come down noticed that one of the stars, this is a red giant, had brightened, but it wasn't this star that brightened, it was some other star right nearby, and it indeed is the nova. And so we had inadvertently obtained a whole series, 5 months of optical light curve of this nova, a unique data set, and right from the beginning too. And we were able to compare with gamma rays because the Fermi telescope was up observing this. The Fermi telescope is usually pointed rather quickly to transient objects like this, which are have potential implications that are very exciting. And what we saw here was the bright peaks and flares in light also occurred in gamma rays. This is very interesting. And it means that the flares in novae were much more energetic than we thought before. In fact, they weren't even seen in X-rays, only gamma rays. They're extremely hot. And down here, you can see that the TESS light curve on the left here shows periodicity. Here's the power spectrum Fourier analysis showing the period of 1.64 hours. So a white dwarf is revolving around another star, which is typical for a cataclysmic variable that produces a nova eruption. And this can happen only once as the star dies. And just before it happened, this periodicity was discovered. So this confirms that it was a so-called cataclysmic variable, a white dwarf accompanied by a low mass star that erupted. What happens is the material from the normal star is accreted onto the surface of the white dwarf, and this accumulates and it becomes very hot because it's very rich in hydrogen. A white dwarf is about the size of the Earth, not the sun. And so it becomes extremely dense. 1 cubic centimeter weighs many tons. And it starts a chain reaction, nuclear reaction, and the whole star explodes, produces a nova. And these are the models based on the data. And there are two possibilities: either protons accelerated at higher energies are involved, or electrons. And it seems that the proton model, because of this point mainly, fits better to the best models here using electrons. So that's too much detail for now. So let me just pass on to my conclusions. And massive stars are those stars which have initial masses greater than 8 times that of the sun. And the interest in them has increased manyfold in the recent decades. Luckily, as it turns out, during the period I've grown as an astronomer, and I can't stop now. Massive stars dominate the light in star formation galaxies, spiral galaxies. They are the most massive stars among the first stars, reaching 1,000 solar masses, we believe, but it remains to be proven. They have produced the first dust and therefore planets. And they are progenitors of 2 types of supernova: long gamma ray bursts, black hole mergers, gravitational wave chirps, and so on and so forth, which I'm sure you've perhaps you've seen, heard something about these exciting objects. And let me say finally that intuition and insight has been my main tool to get started in all these. I see something and I said, it's got to be this, and I've got to prove it. And that's how that has led to some degree of success, I think. So let me just end on a note. This is my wife, Anne, and the bottom left, the Place Ville Marie restaurant up high, enjoying a glass of wine, compared to 1968, a few years earlier, when we were just married, living in Bonn, Germany. And I guess we look a bit younger then. And these are the among the 3 first students I had at the time. They're now senior professors, Laurent and Carmel, who got married at Laval, University of Laval, and Nicole, who is now the director of our physics department at the Université de Montréal. So this is quite nice. And I want to thank all these 3 in particular, because they've been very close with me, and they're very interested in massive stars still. And from and to my wife, Anne, of course. Without her, this wouldn't happen. So here's a list of the students which I've had the fortune to direct, and postdoctoral fellows on the left here, quite a number. And many of them are successful in their careers. And I should note that I'm co-directing 2 PhD students who will finish in a couple of years, 25 to 26, with Nicole. She's my boss now. I was her boss back when she was my master's student, but she's very much my boss now, which is exciting in itself. So let me end on that, and I welcome any questions. Thanks.
Thank you so much, Tony. That was wonderful. We'll open it up for questions. If you stop sharing, you can see the others that are on the Zoom chat.
Sure, I'll stop sharing. New share. Pause share. Stop share. Okay, got it. Okay, good. Thanks.
No worries. Any questions here in the library?
Yeah.
Russell has a question for you.
Hi, Tony. Hi, my name's Russell, and I'm really
Hi, Russell.
Hi, very fascinating. You sold me on this Wolf-Rayet star, and the only one I can remember ever seeing but not knowing what it was in Cygnus. Do you have any recommendations if we want to take a peek for ourselves?
Well, there are 6 fairly bright Wolf-Rayet stars in the Cygnus. I don't know their HD numbers, but I know their WR numbers: 132, 133, 134, 135, 6, 7, 8, 9, and 140. And they're all exciting for different reasons. And if you look, just looking at them with an ordinary telescope as an image, you don't see anything. You have to really look with a spectroscope. If you can put a prism or a grating in front and look at the spectrum, as Wolf and Rayet, the French astronomers, did back in 1867, when Canada was just being born, you'd see these broad emission lines, even at low resolution, spectral resolution. They're so humongous.
So we do have the spectral filter eyepiece, the SA100. Would that give us the variability of the Wolf-Rayet star over time?
No, you wouldn't see the clumps, but you'd see the emission lines, which is already quite exciting because you'd be reliving the experience that Wolf and Rayet had, who discovered these objects for the first time over 100 years ago. Well, 150, I guess.
Good project.
Yeah, definitely.
Yes, that's kind of a neat thing to do. Let me know what happens when you do it, if you do it.
I've had a few students analyze Wolf-Rayet spectra, but we got them from somebody else. We didn't do them ourselves. It's better to do them ourselves.
Yeah, sure. Do you have a means to do spectroscopy with a CCD?
Yeah, not with the CCD. We use the eyepiece filter and just a webcam.
Yeah.
Or
Okay, yeah, well, that's good. Sure, okay, sure.
David, Chris, and Detlev all put a thank you in the chat to you. I'm actually curious about this, the statement that you made about the possibility that Wolf-Rayet stars are the progenitors for dust in the universe.
Yes.
Are we starting to see any evidence of that with the James Webb looking back at those earlier stars yet?
Well, yeah, we're starting, but we have a long road to go because we have to prove it. And the first thing we want to do is to prove that the dust that we saw in this one image, which showed 20 parts of the spiral, 20 repeat of orbits, that's going out to quite a large distance. And it's very suggestive that it may reach the ISM. So, the question is, how many stars are there like this that contribute in our galaxy? And it's believed currently, we've changed our thinking that it's a very important source. It competes with novae and supernovae for forming dust, but only carbon dust. The dust we see in other objects like Eta Carina is silicon-based rather than carbon. There may be some carbon, but mostly silicon. So it's a different kind of dust. And we'll only know after more study what the score is on that.
And these stars are very short-lived. So, I mean, we're only seeing a fraction of what's there now, right?
Well, they're not. It's not that short. The Wolf-Rayet stage itself lasts. The helium burning stage lasts about 500,000 years, whereas the hydrogen burning phase can last about 5 million years on average for an old star, and so it's about 10%. And the helium content of these stars is about 10%. So it's just helium burning, finishing its task, if you like, compared to hydrogen burning, which came before. The next stage of burning, carbon burning into magnesium and neon and so on, up the line, will occur in a much shorter time scale of thousands of years. And the final stage of silicon burning to iron, only a matter of hours. But once that happens, you won't see anything at the surface. It takes a lot of time for the star to adjust and reveal itself. We can only see up to the end of, or the beginning of, and perhaps end of helium burning as the products of nuclear fusion. It's too bad it stops there. And the reason why stars can't burn any beyond iron is that the nuclear fusion reactions become what's called endothermic. They require energy. They don't produce energy. And so that's the end stage. Iron is the heaviest element that can be produced in normal stars. And to produce the elements beyond iron, especially elements like silver and gold and uranium, apparently, and this is a new result, we need gravitational wave collisions between the black holes and neutron stars to do it. All the gold and silver on the Earth, probably, it's believed now, came from these weird stars, neutron stars that have been broken apart because they are fused by black holes, giant black holes, which came from massive stars in the first place. So astronomy is still extremely busy, and it just keeps me up at night, literally. I can't stop. It's just mind-boggling. And I hope I've made some kind of statement to that effect that maybe I've excited some of you, the audience. I hope so.
I have to say, that makes me feel better about the gold standard.
Right. Well, it's a very exotic path to produce it. Nobody would have thought of this before. And it's, again, technology which is driving the science. Inventing new, not only faster and faster computers, which can do far more than ever, but also designing and building devices that can measure variations down to nanometers in size, which is necessary to detect gravitational radiation from these events.
You were mentioning that when Hubble went down, when you had time on it, you switched over and found other telescopes. Are you expecting anything in massive star studies to come from the SKA or from the Vera Rubin coming online? Or
Oh, sure, yeah. Although I'm not involved, I have to draw the line somewhere. I can't do everything. I'll be watching closely what the Rubin telescope will do, looking at the whole sky on a time scale of a day or two, because there's a lot of Wolf-Rayet and other O stars. That's the time scale that they occur on. The more massive the star, the slower the pulsations are.
is there that many more Wolf-Rayet targets in the southern hemisphere like there seem to be from your talk?
Well, the galaxy probably, we estimate it contains about a couple of thousand Wolf-Rayet stars, and we only know about 600 so far. So there are more that are hidden by interstellar dust, the dust that some of them have produced, as it turns out. So I don't have any clear answer to that question.
Santiago has a question as well.
I was just wondering if you're having more fun now in post-retirement than in pre-retirement.
No, it's more of this. I was very excited before because I had a whole flock of students, and each one of them had their own projects. And we had tea every Tuesday, and they would report on this voluntarily with great excitement, and that really turned me on. When I see somebody else getting excited about something that I sort of started or I planted a seed, that really gives me a great satisfaction. But yeah, I would say now my free time, I just spend doing research. I don't teach anymore, and I don't attend meetings of committees and so on. That's all out the window. Thank
If you'd
God.
like to, you're welcome to join us more often. You're
Well,
welcome to come.
I'll do this by giving talks, if that's all right.
Absolutely, absolutely. I was just thinking when you were talking about the bright constellation, that was the other event that was canceled in 2020, was you were going to do a talk about the bright constellation at Marianopolis.
Oh, that's true. Yeah, right. I could still do that if you like. Sure.
I'll reach out
It's
to
all
you.
ready to go. It died because of COVID.
Yeah, no, we just switched online. We just kept going.
Sure. Yeah.
To David and Nicole and a few others, we jumped straight onto Zoom.
Well, as long as you're still interested in Zoom talks, that's what I like to do. It's easier. You don't have to travel. And on a day like today, it's snowing out there. It's not too pleasant, I think, driving, which I would have to do. I live downtown here. And having Zoom means that people from all over the place can join too if they want.
Exactly. We've got Peter, we've got David, we had Chuck.
Yeah, that's fantastic. Yeah.
Anyone else have any last questions or comments? Oh, sorry, Aiden, yes.
I just have a question. You mentioned once they reach iron, the fusion becomes endothermic. What happens after that?
I'm sorry, I missed the first part of the question. I have to turn up my volume a little bit, I think.
You said once they become iron and fusion becomes endothermic,
Oh, yeah.
what happens after that?
After that, the core of the star collapses. It implodes. And that's part of the supernova. The core implodes, falls in on itself, forms a neutron star, or perhaps even a black hole if the collapse is total. And meanwhile, the outer layers, because of the energy released by this collapse of this central core, the outer layers expand. And that's what we see as the eruption. But most of the energy goes into the central core. This release of gravitational energy is converted into heat, and it drives the outer layers in the phenomenon as we know as a supernova, whereas the core, what's left is either a neutron star or a black hole or nothing. Actually, there's a certain interval of mass in which the whole star is blown to smithereens. That's what happens when a white dwarf explodes as a nova. Supernova, actually. Yeah.
That was the type 1A that you talked about in
Yes.
the arena. Yeah.
How is
Right.
our own star's health?
What was that?
How is our own star's health?
Oh, the sun. Oh, well, you know, the sun is so close that to do good physics and explain it is a tough job. And the Parker probe has orbited the sun now a few times at a distance of, I think, 15 or so solar radii, which is really close. So that will produce, and it is already producing very exciting new results about the magnetic field and even close to the sun. Again, technology is the driver. It's as always the way. And of course, the USA is the richest country, is the leader in this. We benefit from spin-offs in Canada, luckily.
Very much. Let's give Tony one more round of applause.
It was a real pleasure. Thanks.
Paul,
Thank
if
you,
you're
Tony.
there, can I call on you to do a thank you?
There he is.
Yes, so I'd like to thank Anthony Moffat for his wonderful talk, and I hope to see everybody again soon in the next public talk, whenever that is.
Thanks, Paul. All the best to you.
Come up to Berger Labonte on March 4th, on Saturday evening.
Oh, yeah, that's it.
If nothing else, keep Russell company in the cold.
I'll be doing a lot of talking fast.
And David, and hopefully later March, we'll do a talk on space places. We're still trying to iron out what the date will be. But stay tuned, keep an eye on your email or on the Facebook page or on the website.
And
So-
sketching, Nicole.
And yes, Nicole's sketching for members on March 23rd. And if you're not a member and you want to come sketching, just email us and you can come as our guest for one of our members' nights.
Mhm.
Thank you, Tony.
Thank you,
Paul,
Tony.
can I ask you?
Yeah. I'll leave you now because I'm so old I have to get to bed soon.